Okay, this is outcome 34, and this has to do with heat transfer. So the situation we're going to do is we're going to use a heat, a solution or a sample by burning fuel. And all you're going to have to do, this is my flame down here, and this is the sample that I'm going to heat. Okay, and it's always going to be different. So essentially what's going to happen is you're going to burn fuel, like for example coal or natural gas or methanol or ethanol or hydrogen or something with a reaction. So we're doing a reaction here. The heat from this reaction is going to be used. The heat from this reaction right here is going to be used to heat our sample up above. So as you can imagine, there's two things that are important: the amount of sample and the amount of reaction. So that's the gist of the whole thing. Now I'm going to erase this and give you a problem here that I'll write out in detail. Okay, so here's the problem. We're going to take 100 grams of methanol, CH3OH, and burn it, and we're going to use that energy to heat 15.500 kilograms of steel. The assumption is no heat is lost to the surroundings. It's a ridiculous assumption, but we're sticking with it. If the initial temperature of the steel is 25 degrees Celsius, calculate, oops, forgot an E there, the final temperature, that's TF here, of the steel. C, and I should have spelled this out, C for the steel is 0.49 joules per gram degrees Celsius. So that is typically given to you. Okay, so the first thing we do is we set up and calculate the energy of this. The reaction for this, which will be given for you, is CH3OH plus O2. It gives us CO2 plus water, and I need to balance it. So that's the reaction. And the delta H of the reaction is given. It's equal to negative 1452. And the units, the signs are important, are kilojoules per mole. So step one, and we'll go over this in class too. So step one is to calculate the heat given off by the reaction. So Q of the reaction, Q is equal to N delta H. You have to give this equation. So the thing is delta H is given, but what is N? So this is just straightforward dimensional analysis. Oh, I missed something. This is kilojoules per mole of reaction on the left. 100.0 grams of CH3OH times the molar mass of CH3OH, which you're going to have to show that. 1 mole of CH3OH per 32.04 grams of CH3OH. And then this is going to be a strange conversion factor. I note that every time this reaction goes one time, I use up 2 moles of CH3OH. So I write in, and we'll put this in a different color, 2 moles of CH3OH for every time the reaction goes 1 mole. So per 1 mole of reaction. We'll talk more about that in class. And then finally, I multiply by my delta H. So I finally got moles of reaction, and now it's negative 1452 kilojoules per mole of reaction. And I'll convert to joules. That'll be useful here. 1 kilojoule per 1,000 joules. And that gives me an answer of, if I did it right, negative 2.266 joules for this reaction. So that's the first step. That's a big, complicated problem, but really it's everything you've done. The only difference is this and this concept of 1 mole reaction is equal to 2 moles of ethanol. In other words, every time this reaction goes once, we use up 2 moles of ethanol, 3 moles of O2 produce 2 moles of CO2 and 4 moles of water. Alright, so I got to erase this. Oops, and I got my calculation wrong, excuse me. It's 2.26 times 10 to the 6 joules. Big mistake there. So I rewrote that. Here it is. Put it in red. Okay, write that down. I'm going to erase and do step 2. So step 2 states that the heat that's produced by the reaction has to equal the heat that is used up or absorbed by the still. So Q loss, we can say this in multiple ways. Q lost is equal to negative Q gain, or perhaps Q gain is easier, is equal to negative Q lost. In this case, Q is a symbol that we use for heat. So we have our heat. So I use this form of the equation, and you got to write this out. Q gained by the heat is equal to negative Q lost, which is equal to negative, what was it? 2.266 times 10 to the 6 joules. That's step 2. So we now know that the heat gained by the still right here is equal to positive 2.266 times 10 to the 6 joules. That's a really easy step, but if you don't show it, we're taking off. Okay, so that's step 2. I got to erase. Okay, step 3. Okay, we use the equation that the heat that's gained by the still is equal to the mass of the still times the specific heat. I'm going to use a symbol C for that, times change in temperature of the still. Books use C or specific heat, S sub H. I don't care which you use. Really, I think our book uses C, but specific heat is better. Actually, I'm going to use specific heat. So I'm going to rewrite this M specific heat delta T. Q gained. Okay? I'd like you to use that instead of the C. So use this equation. Let me erase. So Q equal M specific heat delta T. I'm after delta T, so I arranged the equation. Delta T is equal to Q divided by M times the specific heat. What was our Q again? It was pretty big. 2.266 times 10 to the 6 joules divided by the mass. Now it's the mass of the thing that was heated, not the mass that we burnt. So what was heated was the steel, and it's 15.50 kilograms. So 15.50 kilograms of steel times the specific heat of the steel, which is 0.49 joules per gram degrees Celsius. And I have joule. I got to get rid of my kilograms. They got to cancel. 1 kilogram, 1,000 grams. So my grams cancel, my joules cancel, my kilograms cancel. I have 1 over, I end up with, right here, 1 over degree C, which is equal to degree C. So my answer should be good. Let's see what we get. When I do that whole thing, I get a delta T equal 34.94 degrees Celsius. Okay, so I finally got the delta T. Now I got to calculate T. I got to stop this and erase. Okay, final step, delta T equal T final minus T initial. Rearrange the equation. T final is equal to delta T plus T initial. So that's equal to delta T was from the last page 34.94, and T initial is 25 degrees Celsius. I forgot my units. So that equal T final 34.94 plus 25 is equal to 59.94 degrees Celsius. Okay, that's it. It's a complicated problem. There's a lot of steps, but nothing you can't do.